morning, everyone. You are in the South Seas IJ room, and you are attending the Keystone Engine Next Generation Assembler Framework talk with Quinn. A few things before we start that I need to tell you. Stop by the business hall located in Bayside AB. The Black Hat Arsenal is in the Palm Foyer on level 3, and of course the Arsenal reception at 1700. If you haven't picked up your merchandise today, it's your last chance to visit the Black Hat Swag and Bookstore. And please visit the Cali Linux Lab in Mandalay Bay A. And please put your phone on vibrate if you haven't done that already, so that we won't interrupt the speaker. And without further ado, I present Quinn.
Hello. Good morning, and thank you for being here to see my talk. And okay, so today I give a talk on Keystone, which is a new assembler framework for reversing. And in fact, everything about Keystone, source code, binary package, documentation, tutorials, everything is already available online at that address, keystoneengine.org. So you can go there and get everything you want. Okay, so my name is Nguyễn Quỳnh, and I have some academic background, doing research in one university in Singapore. And I happen to be the founder and maintainer of 3 open source reversing projects: Keystone, Disassembler, Unicorn Emulator, and now Keystone. So that's the question. Anybody here use any of these frameworks? Okay, thank you. Nice to see that. Okay, so first I introduce some background on assembler frameworks, and next how Keystone can fix all the problems on the existing assemblers. And later I introduce a new tool, KeyPatch, built on top of Keystone, and conclusion. Okay, so two years ago, 2014, I introduced in Black Hat the Keystone disassembler framework, which is the one and only open source multi-architecture, multi-platform, multi-binding disassembler for reversing. Last year, I went on and introduced Unicorn Emulator at Black Hat, and this is also the one and only open source multi-architecture, multi-platform, multi-binding emulator for CPU. Now in 2016, we have 2 good frameworks for reversing. We can, from binary, we can decompile using Keystone and get back the assembly. After that, you can do a lot of binary analysis on assembly. You can also feed the binary to emulator and watch the code behavior. So the question is, what is missing here? So you can see that both Keystone and Unicorn, they need emulator at input. They need a binary as input, right? So the question is, how and where to get the binary? And actually, sometimes you need to generate the binary yourself. And that is the missing link here. We need something to, from the assembly, we generate the binary. The binary can be decoded, again by Keystone, or the binary can be sent to the emulator. So what's missing here is the assembler framework. So by definition, the assembler framework is a tool that, given the assembly instruction, it can compile assembly and give back you the binary as encoding. So for example, on x86, if you give inc EAX instruction to assembler, it can compile and return 1 byte, which is 40. And this by 40, when you run that on CPU or on the emulator, it will add 1 to the EAX register. And typically you use assembler to dynamically generate machine code. And after that, you can do binary rewrite, binary patching, or binary searching. Too bad to build a new assembler is just a lot of work. You need to have good understanding on CPU encoding. You need to understand all the instruction set of the CPU. And you need to keep up with the frequently updated instruction, because CPU vendors, they frequently add new instruction from time to time. And it's not easy to keep up with that. So here's my definition for good assembler frameworks. First one is should be a true framework, which means you can build independently build your tool on top of the framework. And if the framework call to an external process to compile the assembly instruction, that's not good, right? So a true framework must embed everything inside, and you can build your tool on top of that. A good framework should support not only Intel CPU, but other architectures, ARM, ARM64, MIPS, PowerPC, Spark, and so on. It should work everywhere on all kind of OS, Windows, Unix, Linux, iOS, Android, and so on. It should be updated. It should support the latest instructions on those CPUs. And it should support many bindings languages so you can easily build your tools on top of that. So you can build your tools in like Python, Ruby, Go, JavaScript, and so on. Too bad that even in 2016, there's nothing up to my standard. There's some open source projects for assemblers, but they are no longer updated. And they have many technical issues. Intel itself has something called XED, which is surprisingly doesn't support many new instructions, which means it missed many new instructions in XED. And that's really surprised me. And there's no framework support on other architectures. ARM, ARM64, MIPS, PowerPC, nothing for those CPUs. So without good assembly frameworks, people struggle for many years. And there's no hope that we can finish that. So usually without good assembler, people write assembly instruction into one external file, and then they call assembler tool on that to generate the object code. But that's not over. You need to call the linker on the object code, and finally you get back the executable file, and you need to parse the executable file to get back the binary. So it's very efficient. And you have little control on the internal process and as output. And course platform support is very poor. So if you want to have assembler for ARM running on Windows, then good luck. There's nothing like that. So I want something good, support on-cap CPU, run everywhere, always updated those latest instructions on all those CPUs, and independent, which means you can build your tools out of that with on-cap bindings. Unfortunately, there's no such a thing, and because I had so much fun with Keystone and Unicorn, I decided to step up again, and that's how I started to work on the Keystone. So the problem is, again, there's too much work if I do that from scratch, because I need to support all those CPUs, a lot of instructions, and note that this one is like, I had very limited resource, because this project started as a personal project. So how I made it? I want to finish this project in few months. Actually, I did that in 2 months. I don't want to take years to work on this. So it's always to stand on the shoulders of giants at the first place, and open source project for community to get involved and contribute. So the idea is fork LVM. Keystone is based on LVM. LVM is an open source project for compiler, so you can build your own compiler on top of LVM very quickly. And LVM is very huge, has very huge community, very active and supported by all the CPU vendors. And it support it run everywhere on all kind of OS. So that's very nice. So LVM is actually very complicated, but we just want to pay attention to one core component named machine code or MC. And around MC, a lot of things in LVM is built, like compiler, assembler, disassembler, debugger, just-in-time compiler. All those things are built around MC. So the reason I fork LVM to build Keystone is that MC support all those assemblers I want. Because the reasons MC need to support inline assembly for compiler. So they have all those assembler for all those CPUs. But note that LVM doesn't support inline assembly for all those CPUs. They support LVM support like 20 architectures now, but they only support inline assembly for like 8 architectures. So for Keystone support only 8 architectures for now. So forking LVM to build Keystone has many advantages. First one, code quality is very good. LVM is very nice project done by professional developers. Assemblers inside LVM is maintained and developed by top experts from each architecture. Like x86 maintained by Intel. ARM64 maintained by ARM and Apple. Hexagon maintained by Qualcomm. MIPS maintained by IMG Tech. Systemz maintained by IBM. All those CPU vendors, they do support assembler for those architectures inside LVM. And Spark and PowerPC developed and maintained by very active community. So the good thing is that new instruction will be updated very frequently and bug fix get in very frequently. So you have like very good code and we support latest CPU instructions. Do you think that forking LVM to make Keystone is easy? Actually, it's not. There's a lot of things to do. First one, MC is like big code and mixed inside like spaghetti. It has many things inside, but I only want assembler, right? So what I had to do is that I spent a lot of time to read the source code of LVM and take only the assembler out, and I remove everything else I don't need. This is the first step. I keep only like parser, code emitter, and ASMR backend for linker, and I tried not to change those components and rewrite some things, rewrite other things for these issues. So the point is that how to make the cut in MC. MC is big code. So if you cut too much, you have to rewrite a lot of code, and it makes it very hard to maintain the code in the future. If you cut too little, then you keep many things that you don't really need inside Keystone. And I think that finally I had some optimal design for Keystone. I make that a proper cut just enough. The second challenge is that LVM itself, when you compile LVM, it has multiple binaries, multiple libraries inside for parser, for table gen, for transformation, everything. So what I had to fix here is that I need to modify the linking setup. So Keystone has only one single library as the output. So the next challenge is that actually the code generated by MC, by LVM, is not consumable, not ready to use, because the code is just for the linker as the next phase in the compiler setup. And for example, you compile that instruction, it just compile return something like those by and AAA after that. AAA means it doesn't know where var1 is. So that's bad because if you do not declare var1, LVM still can compile that code. But in fact, if you run this one on assembler, it should report that var1 is not existed. It should report error, right? So I had to fix something inside the fix up phase of LVM, so it can report the mixing sequence. The next issue is that LVM doesn't understand branch targets. For example, you compile that ARM instruction, you get something on the right side. But the point is that the output is not correct because this instruction, the encoding actually depends on where you are in the memory. And it depends on the distance between where you are and the branch targets. So the output is actually wrong. What I had to do is that I need to view my API so it can specify the rest of the first instruction. And after that, it generates the right encoding for the branch target instructions. Okay, there's one more issue. So if you compile something like that on LVM, you need to report that this instruction is not correct. So you can see that the X on the red instruction should be one number, one constant number. And when LVM sees that, it report error, and after that it exit immediately. And that's not good for the framework, right? Keystone as a framework, when it has some input that it cannot handle, it should not exit. It should keep going, but it report back errors, right? So here I had spent a lot of time to fix all the exits, and I propagate errors back to the high level API, and you return that error to your tools. Another issue is that LVM doesn't support non-LVM syntax, and there's no bindings inside LVM. So what I had to do is that I need to extend the x86 parser to support new syntax like NASM or MASM, and I build all the bindings from scratch. So Keystone has bindings for Ruby, Python, JavaScript, Go, Rust, Haskell, and even OCaml. And here's flow of Keystone. You have parser, you have code emitter, you have linker at the last phase. Okay, so you compare Keystone with LVM, you can see that Keystone is actually quite different. First one is an independent Julia framework. It can understand the current code position, so it can handle relative branch properly. It's much more smaller in size and lightweight in memory. So the size of Keystone is like 10 times smaller than LVM, because I remove everything else that I don't need. Thread safe support non-LVM syntax. It also supports many undocumented instructions that LVM doesn't support, and has a lot of bindings. Okay, so here's one very simple demo. This one is in Python. So you can see how easy it is to use Keystone. Here first you import Keystone, and you specify the rest, the instructions that you want to compile. And then here you set up the engine. In this case, that is CPU, Intel CPU in 32-bit mode. And finally, you compile and you get back the encoding. And later, we print out the result. So it's easy, right? So here's the demo. If you run this one, yeah, so here's the output. Okay, so after I released Keystone like 2 or 3 months ago, people went on to build a lot of things on Keystone. And today I want to introduce my own tool, co-developed with Thành Nguyễn from VN Security. This one's a plugin for IDA. So open source, I already released that at the rest you can see on the screen. This one is allow you to directly do assembling and patching inside IDA. So the reason is that IDA has one assembler inside, but it has many issues. It doesn't support anything but x86, and even for x86, it has many problems. It doesn't support like 64-bit instruction very well, and it meets many things. So here's how it works. So on any instruction you want to change, you just press a hotkey. Control on key. Sorry, screen is not very clear. So you can enter new instruction here. For example, I want to override this one. Pop RBX with other instruction. So we just enter new instruction here. Pop, for example, CX, and patch. And after that, key patch automatically move to the next instruction. So we want to stop, you just cancel here. And you can see this instruction was modified. You can modify this one to, for example, something like push again. Push RAX register. you can see that the old instruction was changed, and key patch automatically patch the next byte with knob instruction. So just another tool inside key patch that allow you to assembler. So for example, this menu support on cap injection on cap CPU. So for example, enter knob here. You can see that knob in X statistic is 90, right? If I change this one to ARM, the encoding is like this. Right? I can change the endian from little to big and see the result change. I can switch to other CPU like MIPS or Spark. Yeah. So key patch has two tools inside. First one is for assembling. So you can use that to compile some assembly instruction, and you can also directly patch your binaries. The good thing that support on type CPUs, 8 CPU now, not only Intel CPU. Okay, there's some other tools I introduce here, but sorry, not much time to left to do demo. Okay, finally, 2016 we have a set frameworks for reversing, Keystone for disassembler, Unicorn for emulator, Keystone for assembler, and all of them are open source, multi-architecture, multi-platform, multi-bindings, and they own function independently, but they complement each other very well to make a full set frameworks, and we call this reverse engineering trilogy. Yeah, here's my conclusion. Keystone is on innovative next generation assemblers, support on-cap 3.1, open source, and future updates is guaranteed because we fork LVM and we can easily update the latest instruction in the futures. By the way, I bring a lot of stickers for Keystone and for all those for all the 3 projects. So if you want to get sticker, please come to see me after my talk. So here's all the links. You can get the source scope, everything here. Any questions? No questions? Okay.
Yeah. I was curious about the patching part. Like, so if you try to patch a bigger instruction, like, what so you can't do that?
Okay. So I give you a tool, and it's up to you to decide what to do. So first of all, it's a new instruction is shorter. There's one option, so we can patch the off-fan bytes with no code. But if the new instruction is longer, it's up to you to decide. You say yes, you didn't patch it, but maybe everything's after that is like messed up and broken.
Okay.
Thank you.